Hello everyone, I am Dr. Jayakumar, St. Xavier's College, Palayangkottai. This is an organic chemistry course meant for MSc Chemistry and the course code is 23PCH11. Now we'll move on to the module. The module discusses what is chirality, what is plane polarized light, what is optical activity, little about what is enantiomerism and RS notation. All these things are covered in this particular module. To start with, what is chirality? Suppose I have a molecule. I have two molecules. They have the same molecular formula. They have the same bond length. Same type of atoms are attached with respect to one another. So what's the difference? Suppose I take that molecule, keep over the other, stacking above the top on the other. By doing so, they don't overlap. This property is called as chirality. And that molecule is called as isomers. Fine. So a molecule is considered to be chiral when they are not superimposable mirror image, just like this. That's why we call it as handedness. Chiral means handedness. This module discusses about that chirality that present in a sp3 hybridized carbon. Now, pay attention to this carbon. So this carbon is surrounded by 4 different groups. So is this the next carbon. So what is the difference between these two carbon? The carbon, when placed over the other, of course, the orange two balls will overlap or they will superposition over the other. So is this blue molecule. They do also superposition. However, here the orange ball, when this molecule is placed over it, it will be green. And this green will indeed turn into red. Therefore, this property is called chirality. And why this chirality happens? This can be very well reasoned by the symmetry aspect. We know that there are 3 symmetrical operations, say reflection, rotation. Rotations could be simpler rotation or complex, otherwise improper rotation, and finding the inversion center. These 3 operations indeed generate 4 symmetry elements. The carbon of question, this carbon did not have any of the symmetry element. Therefore, it is called as asymmetric carbon. Such asymmetric carbon, which is sp3 hybridized, will definitely have the property of chirality. However, there are certain carbons of the given 4 symmetry elements, they may only possess simple axis of rotation, while the rest of the other 3, namely plane, inversion center, improper axis, may be absent. Only in such cases, they are said to be dissymmetric carbon atom. Fine. Such system also undergo or possess chirality. So I'll sum up. Maybe the carbon which is asymmetric will show chirality. However, the carbon of the given 4 elements having only one, that is proper axis of rotation. Rest of the other 3, if absent, such system is called as dissymmetric carbon and that also undergo chirality. Clear? Now, why do we study this chirality property? Because this chiral molecule shows some interesting characters. What interesting characters? The optical activity. So what is optical activity? See, when the chiral molecule was incident with the plane polarized light, then after incident, the resultant light, there will be little twist or otherwise the light get rotated from the line of propagation. See, this is the line of propagation. After incident, the chiral molecule, the right hand of mine, this is chiral molecule. So when the light hits it and comes out, it will get turned or rotate. That's called optical activity. It always happens for a chiral molecule. But provided the light must be a polarized light. That's why we will be discussing what is polar light in the next slide. And the molecule also, the chiral molecule also have some biological significances. Example, amino acid sugars, which is an important biomolecule present in most of the living systems, they're actually chiral in nature. And only certain chiral molecules alone will have some interesting biological characters. Therefore, the chiral molecule or the study of chirality becomes crucial. Apart from that, even the chiral molecule also possess some other interesting characters like say refractive indices or pharmacokinetic behavior. There is a slight change. So that's why the chirality is something very interesting topic in organic chemistry. Now we'll move on to what is a plane polarized light. Looking into the figure, we say it is an ordinary light. When an ordinary light hits on a hits on a chiral molecule, we don't get any interesting thing. However, when a plane polarized light like this one, when incident on a chiral molecule, the optical activity can be obtained. So, how do you convert a ordinary light into an optical light? That's the question. We can make use of a polar light or a polar light or grating can be used. Fine. If you want to get the clear picture, let us known from this figure. Here we have a light, ordinary light. When the ordinary light passes into the polarizer, what happens? Let us imagine the light, ordinary light. What do I mean? See, this is the line of propagation. Light goes by this way. Fine. And for all practical purpose, this is x-axis. So one wave will go in this way, correct? While another wave go in this way. So this is the line of propagation. One wave goes in this way and the next one goes in the other way. So two waves. There could be another wave which is mutually perpendicular to the wave that is going in the x and y. So obviously it must be somewhere slant, mutually perpendicular to this one. That's what given here. One in the x, one in the y, and one in the z. So when such a light was incident in the polarizer, only one wave came out as a resultant wave. That wave is called plane polarized light. Other light, what happened? They get blocked away by the polarizer. Now, when such a polarized light incident into a system with containing chiral molecule, then the emergent ray will have an angle tilted. In other words, the line was certainly rotated to some degree. See, this is the way or this is the angle expected to arrive. However, it gets somewhat tilted by an angle alpha. And why it get tilted or rotated? That's because of the chiral molecule. And this property is called as optical activity. Clear? Now, we'll move into enantiomer. What is enantiomer? I told you chirality means there are two molecules exist together, which is an isomer. What isomerism is it? That is enantiomerism. And that isomer is called enantiomer. What do I say? I have two isomers such that they differ, a pair actually. They differ each other by the way in the spatial deposition. In other words, the one is mirror image of the other. That is enantiomer. Fine. This could be an example. You will be seeing there are two molecules. So the gray indicates the carbon. The red indicates the oxygen. The white small ball indicates the hydrogen. So bond connectivity, bond angle between all the carbon are identical, the same. But how do they differ? Looking at the center carbon, the hydrogen, this is O, oxygen. So the hydrogen and OH are pointing towards us, observer. While in this case, the carbon having the hydrogen and OH is actually the opposite, away from the observer. So spatial disposition is different between the two molecules. Apart from this, you will be able to find any other difference. And this is called isomerism. This isomerism is called enantiomerism. And of course, interesting point is it will rotate the plane polarized light. So do the next one. But interestingly, this will rotate in one direction while the other in the next direction. In other words, both will rotate the plane polarized light not in the same manner, different manner, correct? And thereby we can get the details about which molecule we are dealing with. That's the interesting aspect. And why do we do that? Because this picture of each isomer, enantiomer, are very crucial in developing the drug, as well as pharmacological aspects, biological aspects can be understood by knowing which enantiomer we are discussing. Now, do we have an example? We have an example, that is lactic acid. Actually, this is lactic acid. So what is lactic acid? CH3, CH, OH, COOH. This is lactic acid. Okay, so this is a lactic acid. However, in the middle carbon, the hydrogen is pointing towards us. So is this OH, while here the both are actually opposite. That's the only difference one can find between the two lactic acid. So the lactic acid predominantly exists in a form of enantiomers having two different isomer, which is a pair. And where does lactic acid present? It present in higher mammals, especially in form of milk. Apart from that, it also present in the muscle tissue. Fine. As we said earlier, it exists in a form of enantiomers. One is S lactic acid, the other is R lactic acid. The question is how it is designated as R while other as S. That's the question. So how do you know that? We'll do this RS notation configuration using CIP rule. It is otherwise called as Kohn-Ingold Prolog rule. The Kohn-Ingold Prolog rule is meant to distinguish or name the enantiomer. It follows certain rules that is given in various organic books, especially in a stereochemistry book like Eliel, stereochemistry compounds, carbon compounds, or the stereochemistry by Nasipuri, or any stereochemistry book contains this Kohn-Ingold Prolog rule. I hope you know the rule. So directly we apply the rule and try to get the name of the given molecules. To start with, we'll go with this molecule which is given in the left. So pay attention to the molecule. We are dealing with a molecule in a 3-dimension. Fine. One more time, we have the carbon to the left. While this carbon is at the center, middle carbon, and this carbon is on at the right. Now, the carbon is connected to 3 hydrogens, while the middle carbon having 1 hydrogen, another OH, while the third carbon contains C double bond O and OH, which is a carboxylic acid group. And therefore, the middle carbon is a asymmetric carbon. Why? Because this carbon is connected to 4 different groups, which is a sp3 hybridized. Therefore, asymmetric carbon, it will show chirality. The question is whether will it rotate to the right or left. But it is usually given as L and D, levorotatory or dextrorotatory, L and D. But it is a relative configuration, meaning it is based on the how well it rotates the light to the right or left. But then the Kohn-Ingold belongs to emphasis on absolute configuration. So what is absolute configuration? There is no any reference. We don't take any whether it turns in the light or we keep the glyceraldehyde as a reference. All this considered are not taken into account. However, the molecule, just by glancing it, understanding that it is a chiral center, and we look for the neighbors and we rank them. So this middle carbon is a chiral carbon. So forth, there are 4 neighbors and we have to rank them. But how do we rank? We rank on the merits of their atomic weight. Fine. The higher the atomic weight, the rank priority is 1. Correct. So given here, this is OH, while this is carbon, and the next is also carbon. So there is a tie is happening between the 2 carbon. For time being, we know for sure that O will get priority 1 and the hydrogen will get priority 4. Correct? Because the hydrogen is the least one. Fine. In terms of its atomic weight. Therefore, 1 and 4. Which of the 2 carbons will burn second priority? That's the question. It can be easily understood that the carbon is connected to oxygen while the carbon is connected to the hydrogen. So the tie between the 2 carbons can be broken by the first point of difference. What do I mean? I mean that both are carbon, but indeed it's connected to the oxygen, whereas it is connected to the hydrogen. So there is a point of difference readily arises. So this is 2 carbon, second carbon, priority 2. This is priority 3. Now I'm looking the molecule in the perspective. I'm looking the molecule in the perspective such that the hydrogen is away from me and the oxygen is away from me. So for all practical purpose, this three-dimension molecule is now translated into two. I can directly write R and Rs by looking the molecule in a three-dimensional representation, but for all practical purposes, I'll translate the molecule from three dimension to the two dimension in this two-dimensional representation. One must exercise great care in translating the third dimension into the two dimension. Fine. If any mistake happens here, obviously the result will be wrong. So what is the measure to be taken? Simply write the chiral carbon at the center, and to the left you have methyl, and to the right you have carboxylic acid, and the hydrogen and OH, one on the top, one at the bottom, but they are to be written in the dash form. So this is the dash form, meaning they are away. Now we'll rank it up. This is 1, this is 2, and we have the 3. Correct? Hydrogen is 4. Now, having 1, I am going to priority 2. Fine, COOH. From priority 2, I am going all the way to the priority 3. So 1, 2, 3. This is how I am watching the molecule. When I am watching the molecule, I can realize that my eyeballs going anti-clockwise direction. Correct? Because it goes in anti-clockwise direction and the hydrogen is farther away. Why hydrogen? Because it's the least priority. So when the least priority is farther away and my eyeballs going in a left, from the counterclockwise direction, then it must be designated as yes. However, if it is clockwise direction, that is my eyeball, if goes in a clockwise direction, keeping the hydrogen farther away, the fourth priority farther away, then it must be R, rectus, meaning right hand, while S means sinister. In this example, my eyeball goes from 1 to 2 to 3. Priority 1, priority 2, priority 3, anti-clockwise direction. So it is yes. So the molecule is yes, lactic acid. Clear? Now we'll try it for this molecule. Now in this molecule, of course, this is the chiral carbon because having 4 different groups. What are the 4 different groups? Hydrogen, OH, CH3, COOH. So we are having 4 different groups. It's a asymmetric carbon and it will definitely rotate the plane polarized light, meaning it has chirality. The question is whether it is R or S. If one is yes, obviously the other isomer should be R. Correct? However, we'll try to do. How do we do that? We rank them. How do we rank them? Of course, OH is the highest priority for a reason of having the carbon is connected to the oxygen while the others are simply carbon. So this is having higher molecular weight. So it is 1. And of course, between the two carbons, the first point of differences arises here. So this is priority 2. This is priority 3. This is priority 4. So if I simply bluntly going into the priority wise 1 to 2 to 3, my eyeball once again goes from anti-clockwise direction. Yes, my eyeball goes in anti-clockwise direction. However, so one may instantly say it is yes, just because it is going from counterclockwise, anti-clockwise. Then look at the position of the fourth priority, the hydrogen. The hydrogen is not away from me. It is pointing towards me. Correct? The rule applies. That is, in counterclockwise, it must be yes, applies only when the fourth priority is away from me. But in this case, it is in the wedge, meaning it is pointing towards me. So what do? Whatever the configuration that you obtain should be absolutely reversed. So it is actually seemed to be yes, but then it is R for a reason that the hydrogen is not in the away, vertically down. See, if it is away, it must be vertically down. In the former case, yeah, in the former case, this hydrogen is away from me. So it is vertically down, away. But in this case, this hydrogen is not vertically down, right? Vertically up, meaning it is pointing towards me. Therefore, 1, 2, 3. Yes has to be reversed. So it must be R, right? 1, 2, 3. So S becomes R for a reason that the hydrogen is not vertically down. So it is R. Am I clear? Now we'll try with another example. The next example that we see is a caravan. So what is this caravan? Caravan is a terpenoid, a terpene. And this molecule is present in a large scales in caraway seeds as well as in the spearmint leaves. However, it exists in the form of two isomers, stereoisomers, that is enantiomers specifically, such that one is called plus caravan for a reason that it will rotate the light to the right and the other one to the left. That is, they both will rotate the light in two different ways. And also, interestingly, one will have a spearmint scent while the other will have a seed scent. So this is the two differences between the two molecules. The question is how to distinguish them, name them. I told you, being an enantiomer, they are having two different spatial arrangement, right? This is the two molecules. Okay. How to distinguish the molecule for all practical purpose? We'll take this cyclic system as a base one. By looking at the cyclic system, the methyl group in both the molecules are remain in the plane. However, this group, right, the methyl group, and actually it is a CC double bond. This olefinic group are away. Did you see that? Away. While here it is pointing towards us. So this is how the two molecules are differing each other. The question is how one becomes S caravan. It must be capital S. Fine, because we are doing absolute configuration. Fine. So it's a mistake. Please don't take it carried away. It must be capital S. But how to do that, whether it is S or R, that we'll be discussing now. So for all practical purpose, one more time, these two molecules now translated into two dimension. How do we do that? We simply draw the molecule in the plane. This is below the plane. See, we are the observer. We're looking the molecule. It is away from down. While this molecule is directly pointing towards us. It is up. Remember. And now we'll move on to the next slide. So this is the molecule in the plane. We have drawn the methyl group as it is given. So does this carbon group, everything in the plane. But how do they differ? That olefinic group is bottom down here in this one to the left molecule, while in the right molecule, it is on the top. This is the point of difference. With that, we'll be able to identify whether which one of the two is R and which one of the two is S. We'll do it. Now, how do we do that? We take one molecule as a reference and we number them. See, this is the carbon that we are looking at. So, let us imagine there is a person here, sitting here, right? And straightly looking the molecule in this perspective. So I'm the one looking at the carbon. So, on my head, I will be having this olefinic. And the hydrogen is implied, meaning there is a hydrogen which is not drawn. So, the hydrogen is towards my down. So olefinic group is in up, hydrogen is down. And where is this carbon? This is to the right of mine. Clear? Because I told you I am viewing the molecule in this respect. I'll draw just a minute. So I am viewing the molecule in this respect. Okay. So this is my right hand. This is my left hand. And this is my head. This is my leg. Correct? And now, so by doing that, I will be seeing this is priority 1. Why? Because this is connected to the carbon having double bond. So double bond gets higher priority over the single bond. So therefore it is 1. Which of the two will be, which of the others will rank 2? Make a guess. I'll give you a minute of time. Pause the video and try for it. Okay, I hope you would have tried. Those who come up with the answer, great. Others, please continue watching. So this would be 2. Why this carbon is second? See, we know that the hydrogen is present beneath, implied. It must be the priority 4. However, this is second. Why this is second? Because this is carbon connected to hydrogen. We need connected to the carbon which is having oxygen. But for this carbon, of course, it also contains 2 hydrogen. So we cannot settle. We have to go for the third carbon. It is having carbon, but the third carbon contains oxygen. That's why this carbon is high priority over this one. So this is 2. This is 3. And finally, we have 4. Correct? So our eyeball goes by this way. 1 to 2 to 3. Correct? So how does it goes? So we translate the 3 dimension to the 2 dimension. So here I am standing, I'm watching the molecule here. To my head, I'm having 1. To my legs, I'm having 4. And to the right, I am having 2. To the left, I'm having 3. So I'm moving from 1 to 2 to 3. And the fourth priority is vertically down, meaning it is away from me. That's right. Okay. Because it is away from me, and my eyeball goes from clockwise direction by seeing 1, then 2, followed by 3, it is R. So this is R. If this is R, the other molecule should be obviously S. Correct? Anyhow, you can try for yourself. Thank you very much for the participation.